Signed binary numbers can be represented in three forms: signed magnitude, ones complement, and twos complement. In a signed magnitude system, a number is represented in two parts. So if you want to represent a number is represented in two parts. So here the one part, this part, you call it as a magnitude part, and this part is called the sign part. So this is the magnitude part and this is the sign part, plus or minus. So in this part, the sign part, this is, so here you will this will represent plus or minus, and here the magnitude part will represent the actual number. So let's see an example. If you want to represent plus 9 in a binary form, if you want to represent, so here you are going to represent plus 9 in a 8-bit form. So here this part will be the, so this part will represent the magnitude and this part will represent the sign. So this is for the magnitude and this is for the sign. So for 9 the binary equivalent is 1001, 1001. So I am going to represent in 8-bit form. So 1 bit I am assigning it for sign. So other 7 bits I am using it for the magnitude. So for the equivalent of 9, the binary equivalent of 9 is 1001. So I am putting extra zeros to make a 7 bit. Then this part is allotted for the sign, so it's plus. For plus, we will represent 0, the bit 0 for plus. So bit 0 represent plus, and this is the magnitude, the 9, it represents 9. Suppose if you want to represent minus 9 in a binary form, in a using signed magnitude method, so what will happen is, so here the 7 will be allotted for the magnitude and the 1 part will be allotted for the sign. So it is same like the previous thing, plus 9, the magnitude is same. The magnitude of plus 9 and minus 9 is same. Now for the sign, it is minus. So the sign for minus is, the bit for minus is 1. So for plus, the sign bit is 0. For minus, the sign bit is 1. But the magnitude will be same. So here plus 9 will be in true binary form only. So when you in 8-bit, when you represent a binary number in a true form, as a true binary number, when you represent, it will be equivalent to this. So when it comes 1 in the front, means its meaning is it's minus 9 in a sign magnitude system. Ones complement method. When arithmetic operations are implemented in a computer, it is convenient to use complement methods rather than signed magnitude method. In signed magnitude method, we use a separate bit called the sign bit to represent whether a number is positive or negative. But in ones complement method, we don't use a separate sign bit. Suppose if we represent a number 9 in a true binary form, in an 8-bit number, as an 8-bit number, I am going to represent number 9. Okay, this number is represented in a true binary form. So suppose I want to now find plus 9 for in 1's complement form. So for plus 9 in 1's complement system, how will I represent? We'll see. So this is plus 9 is represented in this way, and this is equal to the true binary number. So 9 is represented like this, and plus 9 in 1's complement, it's represented in this way, and this both are equal. That is the 1's complement of plus 9 is equal to the true binary number of 9. So for minus 9, there will be a change. So minus 9 is in a 1's complement system. It is obtained by changing all the zeros to 1's and 1's to 0 of the true binary number. So from this you have to change all the zeros to 1's and 1's to 0. So when you do this, you get this. So you're complementing the all the numbers in the true binary form. So you get the minus 9. So 1's complement is very good to use to represent negative numbers. So both in sign magnitude form and as well as in complement form, the positive numbers are equal to the true binary numbers, but there is a change only in the negative numbers. 2's complement method. Let's see this with an example. For a number 9, the binary number will be in 8-bit form 1001. So this number is in true binary form. So to represent 2's complement of plus 9 is, this is the 2's complement of plus 9, and this number is same as the true binary form, and also this plus 9 is for the equivalent binary equivalent is same as the for the 1's complement form, and also it's equal to the sign magnitude form. So plus 9, so from this we can say a positive number is same in all the three forms, that is in sign magnitude form, in 1's complement form, and in 2's complement form. The positive numbers are all same, and they are equal to the true binary numbers. And if we want to represent a negative number, suppose for example minus 9 you want to represent, what you do here is, first you have to find the 2's complement of the true binary number. So 2's complement of this number will be, first you have to find the 1's complement of the number of this number, you have to find the 1's complement, then add 1 to it, so you will get the 2's complement. So the 1's complement of this number will be changing zeros to 1's and 1's to 0. So this is the 1's complement. 1's complement. So I need 2's complement. So I add 1 to it. So when I add 1 to it, so I get 1. When I am adding 1 and 0, so I will get 1, then 1, 1, 0, 1, 1, 1, 1. So this is the 2's complement for minus 9. So these are equal. So for 2's complement is very well used to represent negative number, but the positive numbers are same as the true binary form. Only the negative number will be different. Among sign magnitude system, 1's complement system and 2's complement system, the most commonly used system is 2's complement system. So let's see why 2's complement is very efficiently used. Let's take a example. For plus 0, the in sign magnitude form, it is represented as 0, 0, 0, 0. Here this first 0 represents the signed bit, and minus 0 is represented as 1, 0, 0, 0. Here 1 represents the sign bit minus. In true form, we will represent 0 in a true binary form. 0 is represented as, this is the normal way we represent a binary number. We are representing all in a 4-bit form. So here plus 0 in sign magnitude form is similar to the true binary form. Only minus 0 is different. Now for plus 0 in 1's complement form is 0, 0, 0, 0. It's also equal to the true binary form. For minus 0 in 1's complement form, just we are converting the zeros to ones. So this is the in 1's complement form. And in 2's complement form, 1, 0 is this, and it is equivalent to the true binary form. So from here you can see for a positive number, in all the system, the binary numbers are same. So for positive numbers, all the binary numbers are same in all the systems, and they are equal to the true binary form. And for negative, for minus 0 in a 2's complement, we have to find the 2's complement of the true binary form number of 0. So we have to first find the 1's complement, then add 1 to it. So the 1's complement of this 0 is, you have to just change the zeros to 1. Then this is 1's complement. Then how will you get 2's complement is, you have to add 1 to it. So when you add 1, you will get sum 0 and carry is 1. Again when you add 1 plus 1, the sum is 0 and again carry is 1. When you add these two, sum is 0 and carry is 1. When you add 1 plus 1, sum is 0 and the carry will be 1. Just we can neglect the carry because here we are representing in a 4-bit form. So this is the answer. So the 2's complement of minus 0 will be this. So from this you can understand that in 2's complement, the zeros in negative and positive form, they are same. You know, for zeros there is no negative or positive. If negative or positive, both are equal to 0 only. So in 2's complement form, the zeros are in both negative and positive, they are same. But here in 1's complement and in sign magnitude form, there is a change. There is for 0 there are 2 representation, but in only 2's complement form, 0 is represented in only one form. Minus 0 and plus 0 both are 0, so they are represented in only one form. So in 2's complement is very commonly used system.